here we're looking at y equals sine inverse of x, and our goal is to find its derivative. And before we do that, let's make a sketch of it. So we know what the graph of sine looks like, and in order to get the graph of sine inverse, we need to switch the x and y values of sine and restrict our domain to the interval -1 to 1. And the range goes from -pi/2 to pi/2. And we know that the sine of 0 is 0, so sine inverse of 0 is 0. We know that the sine of pi/2 is 1, so the sine inverse of 1 is pi/2. And we know that the sine of -pi/2 is -1, so therefore sine inverse of -1 is -pi/2. And there's the shape of sine inverse. So the way we're going to find the derivative of this function is we're going to use what we know about inverses, which is that if y equals sine inverse of x, that means that x equals the sine of y. And the reason we're doing that is we know the derivative of sine, and we can use implicit differentiation to actually solve for dy dx after we take the derivative of both sides. So we'll take the derivative of both sides of this. The derivative of the left side is just a 1. The derivative of sine of y is cosine of y, but then you get a times by the derivative of the inside, the y, dy dx. And then we solve that for dy dx. So dy dx is going to be 1 over cosine of y, which you could write as secant of y, I guess. Secant of y. Alright, so that's not bad, except we would like this derivative to be in terms of x, not in terms of y. So we've got to go get an expression for the secant of y, which we can do. So I'm going to go over here and actually make a triangle, because if we're taking the secant of y, that means y must be an angle. So I'm going to just draw a triangle here. We'll assume it's in quadrant 1. So y is an angle, because I'm taking the secant of that angle. And, well, what else do I know? Actually, we can go back to this relationship. Sine of y is x, right? The sine of y is x. So if the sine of y is x, I could also say the sine of y is x over 1. And by definition of sine, opposite over hypotenuse, that must be an x and that must be a 1. And then I could use the Pythagorean theorem to solve for this bottom side, which would produce this. So now I've got all these sides in my triangle, and I can find the secant of y. So the secant of y is just the reciprocal of the cosine of y. So the cosine of y would be adjacent over hypotenuse, which means that the secant would be hypotenuse over adjacent, or 1 over the square root of 1 minus x squared. So there is the derivative of sine inverse. And notice it agrees with our picture here. So for instance, you can't plug in a number bigger than 1, because if you do, then your denominator is going to have a negative under a square root. You can't plug in anything less than 1, less than -1, because again your square root would have a negative underneath. When you plug in 1, the bottom becomes a 0, which implies we have a vertical tangent, which is what happens at 1 and -1. So it looks like our derivative is agreeing with our picture, which is always a good sign. But this is if you take AP Calculus, this will be one of the derivatives you want to memorize. The derivative of sine inverse is 1 over square root of 1 minus x squared. We got the derivative of sine inverse. Now let's find the derivative of tan inverse. So tan inverse has tangent of x has asymptotes at pi/2 and -pi/2 on the x-axis. Those are vertical tangents. Those are going to become horizontal tangents for the inverse. The tangent of 0 is 0, so tan inverse of 0 is 0. And then we know that we know how tangent approaches the asymptotes, right? In between 0 and pi over 2, tangent starts approaching the asymptote pi over 2 at pi over 2. So we know our shape's going to look like that. So our domain is negative infinity to infinity, and the range is negative pi over 2 to pi over 2, not including those endpoints. So we're going to use the same technique we used to find the derivative of sine inverse. We know that if y equals tan inverse of x, that must mean that x is equal to the tangent of y. And we know the derivative of tangent. So we'll use implicit differentiation here. The derivative of x is 1. The derivative of tangent is secant squared. And then I get it times by the derivative of the inside, dy dx. And so that must mean if I solve for dy dx, it's 1 over secant squared, which I could also write as cosine squared of y. Now that's in terms of y. We'd like it in terms of x. So let's go back to a diagram of a triangle. We know that x is the tangent of y. That must mean y is an angle. And by definition of tangent, tangent is opposite over adjacent. So if tangent is x, I can write that as x over 1. And then by the Pythagorean theorem, this hypotenuse would be the square root of 1 plus x squared. And that means that I can evaluate the cosine of y, because the cosine of y is adjacent over hypotenuse. So it's going to be, cosine of y cosine squared of y is equal to 1 over the square root of 1 plus x squared, which is equal to 1 over 1 plus x squared. And that's the derivative of tan inverse. And a couple of things you may notice. One is, as x goes to infinity, the derivative goes to 0. And that makes sense because you can see that as x goes to infinity in the graph, the slopes become more and more approach horizontal. Same as if you approach negative infinity, right? As x goes to negative infinity, the derivative from the equation approaches 0 because the denominator is getting really big. And as we go towards negative infinity on our graph, we can see that the tangent lines start to approach horizontal. When you plug in 0, you get a slope of 1. That looks pretty believable. Looks like the slope at 0 is 1. And so now we've got the derivative of two inverse trig functions. And these are, for those who take AP, these come up a lot, these first two, sine inverse and tan inverse, so they're worth memorizing, or at least remembering how to rederive. Here we'll look at the derivative of secant inverse, kind of a less common function that shows up, but we'll look at it anyway. First of all, we'll remember that the secant graph has a vertical asymptote at pi over 2, which means that this graph is going to have a horizontal asymptote at pi over 2. We know that the secant of 0 is equal to 1, which means that secant inverse of 1 must equal 0. And we also know that the secant of pi is equal to negative 1, which means that secant inverse of negative 1 is equal to pi. And then we know that secant is not defined on the interval, or has no output values in between 1 and negative 1. And we know that it has to approach the asymptotes. So this is the graph of secant inverse. So we can see its domain is negative infinity to negative 1, union 1 to infinity. And we can see that its range is from 0 to pi over 2, and then from pi over 2 to pi. So as usual, we're going to find the derivative by writing our relationship, but then switching the perspective and saying that this means that secant of y is equal to x. And then we take the derivative with respect to x. The derivative of the right side is a 1. The derivative of secant is secant tangent. So it's going to be secant y tangent y, and then using implicit differentiation to take the derivative of the inside, dy dx. So that means dy dx equals 1 over secant of y tangent of y. And again, we want to go express this in terms of x, not y. So we'll draw a triangle. And the secant of y is x, so y is an angle. And if the secant of y is x, that means that the cosine of y is 1 over x, which means that I must have a 1 here and an x here. And then by the Pythagorean theorem, this side is square root of x squared minus 1. And so the secant of y is equal to x, and the tangent of y is equal to square root of x squared minus 1. Now it seems like we're done. There's one flaw in this, and that is that if you look at your graph, right, the slopes of secant inverse are always positive. Right? There is no tangent line you can draw that would have a negative slope. However, if I plug in a negative x value into my derivative, I'm going to get a negative number, right? Because if I plug in negative 2, for instance, this x is a negative, and underneath the square root will always be positive for any number you plug in the domain. So that's a problem. We actually want our derivative to always produce positive slopes. And so what that means is we really just need this x here to always be a positive number. Whatever we plug in, we need it to be positive. So we can fix that by making it the absolute value of x. So the derivative of secant inverse is really 1 over absolute value of x. And that will allow us now to plug in, for instance, negative 2, and actually get a positive slope, which is represented by our graph. So there is the derivative of secant inverse. And now we've got the derivative of sine inverse, tan inverse, and secant inverse. The other three are really easy to derive. I'll do that quickly in another video.